Have you ever wondered why the readings from a temperature sensor or a pressure gauge are not always perfectly precise, even with modern technology? It is a common challenge in embedded systems, where real-world measurements need to be translated into accurate digital values. A system accounts for sensor input-output linearity primarily through a process called calibration, often combined with mathematical modeling and signal conditioning. This ensures that the sensor's output accurately reflects the physical quantity it is measuring across its entire operating range. The core reason sensors exhibit nonlinearity stems from the physical principles and material properties upon which they operate. For instance, the resistance of a thermistor does not change perfectly linearly with temperature. It follows a more complex exponential relationship. Similarly, strain gauges might have nonlinear responses at higher stress levels due to material fatigue or stretching limits. These inherent physical characteristics mean that a simple proportional relationship between input and output is rarely achieved in practice, necessitating these compensation techniques. To address this, embedded systems employ several practical techniques. One common method involves using a lookup table, where a microcontroller stores a series of known input values versus their corresponding sensor output values. When the sensor provides a reading, the system interpolates between the stored points to find the corrected input value. Another powerful technique is polynomial regression, where a mathematical equation, typically a second or third-order polynomial, is derived during calibration to model the sensor's nonlinear transfer function. This polynomial is then used in real time to convert raw sensor data into linear measurements. For simpler cases, piecewise linear approximation can be used, breaking the sensor's operating range into smaller segments, each approximated by a straight line. Additionally, active compensation circuits, using operational amplifiers, can be designed to electrically linearize a sensor's output before it reaches the analog to digital converter. Understanding terms like linearity error, sensitivity, offset, and span adjustment is crucial here. Linearity error quantifies the maximum deviation of a sensor's output from its ideal linear transfer function. Sensitivity refers to the change in output per unit change in input. Offset is the output when the input is 0, and span adjustment scales the output to fit a desired range. Advanced systems often perform a two-point or multi-point calibration, measuring the sensor's response at both the lower and upper ends of its expected operating range, and then at several points in between to characterize its nonlinearity more thoroughly. By diligently applying these calibration and linearization techniques, an embedded system can overcome the inherent imperfections of physical sensors. This meticulous approach transforms raw, potentially nonlinear sensor data into reliable, accurate information, which is absolutely vital for precise control, dependable monitoring, and the overall robust operation of countless applications, from medical devices to industrial automation.